we can move to the next speaker.
Okay, I will introduce next speaker. Next speaker is Professor Kyoung Moon. Dr. Moon is professor at Yale University School of Architecture. He received a PhD from MIT, and he worked as an architect at SOM in Chicago. Dr. Moon's primary research area is integration between the art and science and technology of architecture with focus on tall building. Actually, he is a bridge person between the architecture and structure on tall building committee. Okay, please welcome next speaker, Mr. Moon.
Thank you for coming to the session. My name is Kyoung Moon, and then I'm at Yale University School of Architecture. And today's my presentation topic is diagrid structures for twisted, tilted, tapered, and freeform tall buildings. Considering the pretty long history of architecture, the history of tall buildings is pretty short. It's only about 100 years, a little bit more than 100 years. But with that very short history of tall buildings, I'm not sure if we can say is an infant or teenager, as was briefly mentioned by the Mr. Pedersen last night. But within that very relatively short time period, this tall building have experienced numerous different stylistic transitions, and then that stylistic transitions over the 100 years kind of produced many different building forms, as you can see in this diagram. My study about the complex shaped tall buildings began with the classification of tall buildings depending on the building forms. As you can see here, there are many different building forms, and then there are variations and combinations. And it was a very challenging task for me to even just classify tall buildings depending on their form characteristics. So for now, I decided to go with more kind of general and then broad category of tall building forms, which is also accepted by many people. So as my presentation topic says, that's just the twisted, tilted, and tapered, and free forms. So basically 4 form categories. And then, as was the case in the building forms, the structural systems for tall buildings, there are many different tall building structural systems developed specifically for tall buildings. Among them, diagrid structures, which is kind of more recently emerging, has been one of my research topics for the past several years. And then diagrid structures with their unique compositional characteristics, it's a very architecturally kind of unique structure and then many potentials architecturally in any existing orthogonal urban context in general. And structurally also, this is very efficient structural system for especially tall buildings because of this axial actions of all the diagonals in terms of carrying lateral load. So this presentation today is about employing these diagrid structures for complex shaped tall buildings and then study their basic characteristics, how these diagrid structures perform in more recently developed complex shaped tall buildings. And this slide shows the workflow diagram, how the work was performed. As you can see here, in order to investigate the impact of the various geometric configurations variations, such as the rate of twisting, the angle of tilting, and then the rate of the fluctuation of the freeform, such and such on. So I began with the parametric modeling. Parametric modeling using Rhino and Grasshopper, and then the models were exported to structural engineering software. In my case, I used the SEP 2000, which is very popularly used in the United States, probably in Korea as well, I believe. And the first category is the twisted tower. As you can see, these picture shows several examples. First one is, as everyone knows, this is Chicago Spire, designed by Calatrava. And then second one is the Infinity Tower by SOM. And then third one is the one of my students' design work for the design studio project, which I'm leading. And so this is the diagrid structure. None of these structures, existing buildings and the student design work, didn't use the diagrid structures, but this particular study I'm presenting today employ these diagrid structures for these twisted forms first. And this is the design methodology I developed several years ago and then presented in the Dubai Congress of the CTBUH. Of course, I'm not gonna go over these numerical things here, but basically I use this same stiffness-based design for more complex shaped tall buildings employing diagrid structures. And this is the some of the study models of 60 stories whose aspect ratio is about 6.5. And then the first one is the first one is just the prismatic diagrid structures, and then the second one is the all different rate of twisting, 1 degree per floor, 2 degree per floor, and 3 degree per floor. If these structures are all solid, for example, just considering this all solid object-like structure, then the moment of inertia of this solid object is all the same. So for example, you just push it at the same identical concentrated load at the top. In terms of the solid object, then the lateral deformation should be all the same. But the building type structure is not solid. It's composed of all different frame members, many frame members. So once you begin to twist the building, composed of many frame members, then the frame is kind of all shaping differently, meaning that the vertical columns becomes slanted columns. So in this case, diagrid angles keep changes as you twist the building. So as you can see from this maximum deflection at the top of the structure, as the rate of twisting increases, the deformation of the structure increases, which means the lateral stiffness becomes smaller and smaller as you twist more and more of the building. The next factor which affecting the structural performance of these twisted buildings is not only the rate of twisting, but also the height of the building. More importantly, the aspect ratio, height to width aspect ratio of the building. So the previous slide showed the 60-story building with the aspect ratio of 6.5, and then this is the 80-story case with the aspect ratio of 8.7, and then this is the 100-story building with the aspect ratio of 10.8. And this is a study result, all combined together. As you can see, for all twisted diagrid structures, the stiffness of the diagrid structure reduces as you twist the structure more. In terms of the relationship between the height of the building, very similar situation you can observe. So the stiffness reduction ratio is not that much sensitive to the building height in diagrid structures. Actually, I performed this complex shaped tall building study with various different structural systems, and then this presentation is only focusing on the diagrid structures. And briefly, as a comparison between diagrid structures and other structures, I just selected the another study with the brace tube system, which is quite similar in terms of carrying lateral load by axial actions of the columns and then bracings. And this is the quick study result with the brace tube systems, also kind of twisted, 1 degree, 2 degree, and 3 degrees per floor. And then in terms of building height, 60, 80, and 100-story building. If I put diagrid and then brace tubes together, you can see the similarity and then differences. As you can see, as the building has more twisted late, it loses its lateral stiffness, and then the maximum deformation keep increases. But in diagrid structure cases, the stiffness reduction is not that much sensitive to the building height change. But if you see this, I'm not sure what this pointer is not working well, but if you compare this diagrid, which is kind of a solid line versus the dotted line of the brace tube case is much more sensitive in terms of lateral stiffness reduction depending on the building height, which is related to the geometric configuration of these two different structural systems. The diagrid structure studied in this case, as well as in most cases, is composed of only diagonals, which are already angled, but the brace tube is composed of vertical columns and diagonal members. Of course, vertical members carry primarily overturning moment on the flange side vertical members, and then the shear forces are carried by the web side bracing members. But if you begin to twist those brace tube structures, there are eventually no vertical members. It's all slanted members compared with the diagrid structures, which from the beginning composed of all slanted members. And next case, the tilted tower case, and these are some examples. The first case is the signature tower, formerly known as Dancing Tower by Zaha Hadid, and second one is the Gate of the Europe Tower by Philip Johnson, and third one is the recently completed Helmut Jan's Beer Tower in Las Vegas. Very similar study was carried out with the tilted buildings employing diagrid structures, and then the first one is the straight prismatic diagrid tower, and then second one is without no floor offset. It's very similar to the Gate of Europe Tower or the Beer Tower case in terms of geometric configuration. Of course, the towers I previously showed did not use diagrid structures for their structural system. And then this case 1.3, 1.4, and then case 1.5 is similar to the Zaha's signature tower case. And this is just a quick basic study result in terms of how lateral stiffness changes and then how the maximum lateral displacement changes depending on the rate of the tilting. And in terms of the wind load induced lateral displacement of tilted tower employing diagrid structure is not substantially changing depending on the rate of the angle of the tilting. But as you can imagine, the tilted towers are initially deformed by gravity load, and then that gravity load induced lateral deformation becomes larger and larger as the angle of tilting becomes larger. And as you can see here, this is the gravity load induced lateral deformation, and then at some point even this displacement is bigger than the wind load induced lateral deformation. And another consideration in terms of the previous graph was based upon the wind load, which is parallel to the direction of the tilting. But if the wind load is coming from the direction perpendicular to the direction of the tilting, then based upon this eccentricity, this building gets kind of twisted. And some basic comparisons between the diagrid and then other structural systems. In this case, three cases: brace tubes and outrigger structures. Kind of interesting study result here is that this is the blue is diagrid, and then red is brace tubes, and then green is outrigger structures. About this is lateral displacement in terms of the wind load. As you can see, brace tube and diagrid, the lateral stiffness does not change much depending on the angle of tilting, but interestingly, these outrigger structures, if you tilt the outrigger structures, its lateral stiffness is actually increased This is because this is the basic configuration of the oligo structures I studied. Stiff braced core, and then this is oligo trusses, and they are mega columns. Initially, they don't make this mega truss-like triangulated configuration. But if you tilt the building, then these three major components, braced core and mega columns and then oligo trusses, make very large mega trusses. So that kind of impact in adding this lateral stiffness, as you can see in this graph. And tapered case is very popular and then has been used for a long time. And then as Mr. Poon explained, no building is kind of going upward larger. It's all kind of tapered to the top. And very logical situation for tall buildings. And then John Hancock Center, of course. And then this is the previous scheme of Lotte Super Tower designed by SOM. And this one is Fair Tower in La Défense area of France. All tapered forms. And prediction of structural performance in terms of lateral stiffness of tapered tower is pretty simple and easy, but of course the lateral stiffness increases as the base becomes larger and then kind of narrower top. But some considerations when diagrid structure is used for tapered buildings. If the diagrid module height is not changed, then if you taper the building, then the diagrid angle keep changes, and then the angle becomes steeper as it goes to the top of the building, based upon the configuration of the diagrid, which is kind of adversely impacting the lateral stiffness of tall buildings with the shallower diagrid angle at the bottom and then steeper diagrid angle at the top. So better situation because that's because the bottom portion of tall buildings is governed by the overturning moment and the top portion is by the shear forces. So if we want to make it more structurally corresponding angle configuration, then more steeper angle should be at the bottom and then more shallow angle should be at the top. Which was actually the example of this Lotte Super Tower designed by SOM as well. So a couple other options in this case. The second group is the making the diagrid structures by adjusting the module height, more like a uniform angle configuration, close to uniform configuration. And then this bottom case is kind of adjusting more of the diagrid module height so that the shallow angle goes at the top and then the steep angle goes at the bottom, which is kind of more corresponding to the basic structural phenomenon occurring at the tall buildings. And this is the result in terms of lateral displacement. And then without any adjustment, but still based upon this tapered form, if you taper more and more, then stiffness becomes larger and larger. But if you adjust the angle, as you can see from the red and green, the stiffness becomes even more larger. But in this 60-story case, it's pretty similar. The second group and third group. Some more studies with the 80 stories and the 100 stories. And then the effect of adjusting the angles, that means again more stiff angle at the bottom and then shallow angle at the top, becomes, you can clearly see that impact from this much higher tall buildings, 100-story buildings. Now you see the red line and then green line is kind of separated, and then that the more structurally following angle configuration gets more stiffer. And the last group I'll present is the freeform towers, and then the first one is again the fair tower, freeform and then tapered, and then the next one is the capital gate tower, and then the third one is one of my students' design work, all freeform towers. In this case, you can see other examples I showed for the twisted, tilted, and tapered towers. There are no existing examples using diagrid, but in terms of freeform towers, of course, the fair tower was not completed yet, but it was originally designed with this diagrid. This building, I believe this building was completed already with these diagrid structures outside. Of course, this one has the concrete core inside as well. And my students' work from the beginning began with these diagrid structures, because diagrid structures, considering the characteristics of the diagrid structures, is pretty good system to better define free-form tall buildings. If you try to define any irregular free-form with conventional orthogonal frame, for example, defining any irregular free-form with 4 points will be very, very vulnerable to distortion in terms of defining and then kind of carrying out the construction. But by using the diagrid structures, which is based upon its original characteristics, or triangularization. So using 3 points is much easier, as well as much accurately define any irregular freeform. So probably that's the reason you can see diagrid structure is used from the beginning for these freeform structures. And these are some studies about the facade treatment and then generating the freeform structures. Actually, these are freeform-like structures. This is not absolutely freeform. You know, to model this thing, I used the many different sine curves in different ways, so that this is kind of not exactly freeform. But in variation, in this case, is the fluctuation, the deviation from the original rectangular box form, how much it is deviating. That's the parameter I used for this study. That is shown as this plus minus delta, and this large delta is the lateral deformation. So the first case is the straight case, and the next one is the deviation is plus minus 1.5 meter. The second case is plus minus 3 meter deviation from the original box form. The third one is the plus minus 4.5 meter from the original box form. And in this building case, the original box form building, the core perimeter to actual building perimeter is 9 meters. So the building form deviation is fluctuating from 0 to plus minus 4.5 meter case in this case. And clearly, again, if you fluctuate more and more of this building form from the original box form, it kind of loses its lateral stiffness more and more. And this is the 83 structure case. It's very similar. This study is not finished yet, so I'm not presenting any graph, kind of combining all these cases. This is still ongoing. And this is my last slide, and then I kind of like to finish my presentation usually with the collage of my students' design work, as I appreciate and then as I kind of proud of my students' effort and enthusiasm to learn how to design better performing tall buildings. And then as I see the President Kim's face here, of the Chang Minu. This research was supported by Chang Minu, structural consultant. I appreciate their generous support for this research. Thank you.
Okay, thank you. He gave a good structural solution for freeform structure. We have some few time to receive 1 or 2 questions in plural. Is there any some question? Okay. Would you?
My name is Ho from Hong Kong. In your study on the tilted structure, especially on the tilted structure, I just wonder whether you have considered the P-delta effect in your study, especially the one you saw for the braced tube, diagrid, and the outrigger. And I'm a bit surprised the outrigger result is much better than the braced tube and the diagrid.
In terms of preliminary member sizing, I didn't use the P-delta effect. I just select the member size based upon the methodology, stiffness-based design methodology. It's pretty simple, very, very simple, very approximate methodology. So I put those member size in my members, and then when I run the SAP program, I turned on the P delta effect. So that was considered in terms of actual analysis using computer software.
Okay, one more question there.
So you check the cross windness displacement for the tilted and also the helicopter type.
Yeah, but these are
only for along wind.
Only for the static response. The dynamic response, as you probably were asking, the
So
across
crosswind
direction,
is not considered.
That's dynamics.
Okay.
If you are here, and then that kind of thing will be presented by Chang Min-woo in the afternoon, I believe. I kind of made these models for many different studies, and then dynamic response of these structures are developed by some other groups. So you can see those presentations in the afternoon session, I believe.
Okay, thank you. Okay, you have.
I have one question. For tilted structure, there is some deformation, lateral deformation under gravity.
Mm-hmm.
There is deformation under gravity load. And this deformation is increased because of the long-term effects. How could you deal with this induced or maximum or lateral deformation, especially with the surfaces? We have surfaces running like lifts, like pipes.
I'm sorry, I don't catch your... I mean, you are talking about the gravity-induced deformation, right?
Yes.
Basically,
yes.
I believe the gravity-induced deformation can be resolved pretty much during the construction process if planned very carefully, which is pretty common.
Okay, but it will increase with the time. That's what I mean.
Hmm?
It will increase with the time. After construction, you will still have some deformation. Because of long-term effect, after construction finishing, you still have deformation.
Of course, there will be much more stresses based upon this tilting, based upon the gravity load. So that's another concern, actually. There will be more deformation as well as kind of very concentrated stresses at the side of the tilting. I mean, the most vulnerable side of the tall buildings is the side where, I mean, this is the tall building, and if the wind is blowing this direction, the most vulnerable side is this side, right? The compression side. The compressive force from the gravity load combined with the compressive force from the lateral load makes this side very, very vulnerable in terms of stress and everything. And then if the building is tilted in this direction, that stress becomes even much more greater. So that's kind of consideration. I'm not trying to make solutions for these things. I'm just trying to begin some studies because these buildings are all complex shaped building forms are just to keep growing and growing. So I'm just beginning my study about these more complex shaped tall buildings.
Okay, thank you.
Okay. Thank you. Thank you. So good presentation. Let's give him the back.